Hello everyone, my name is Shujiang, a PhD student from Johns Hopkins University. Today, let me introduce our paper, Rendering Contention Channel Made Practical in Web Browsers. First, let me introduce what is the rendering contention channel. For example, if we open two pages on the same computer, page A and page B, and both page has rendering task. Page A has a lower rendering workload, like rendering 100 elements, and page B has a high rendering workload, like has 10,000 rendering workloads. And when we draw a graph, the x-axis is time, and the y-axis is rendering time per frame. Because page A has a low rendering workload, the page A has a low rendering time per frames, and page B has a high rendering time per frame. When page A and page B has a stable rendering task, the rendering time is also stable. After that, when page B decreases the rendering workload from 10,000 to 1, the rendering time of page B will become lower. Also, even if the page A has a stable working task, the rendering time of page A will still comes low. When page A increases the rendering workload from 100 to 20,000, we can both page A and page B rendering time will become higher. It means page A and page B are influenced by each other, and they share some resource, and this is the rendering contention channel. After introduce what rendering contention channel is, we infer the reason. We design a methodology, the single variable testing, to infer the reason. We have three parts: sender, observer, and noise generator. Sender run a ground truth workload. Observer compare what being measured in the channel with the ground truth to compute the signal to noise ratio, is the SNR value. And the noise generator change one parameter, like the frequency, thread number, CPU, GPU workload. If we draw a SNR and variable graph, when the line comes lower, it means this parameter influence the rendering content channel. If the line is flat, the parameter does not influence the channel. Before that, let's talk some background about the rendering resource. On the hardware level, we have two different rendering. They are the hardware rendering and software rendering. In our analysis, we found CPU, GPU, screen buffer contribute to hardware rendering, and CPU, screen buffer contribute to software rendering. So we start with the hardware rendering. We test on the Chrome and test on 4 different machines. For CPU, we test on the frequency and the thread number. According to the SNR value, we found CPU contribute to the hardware rendering. Also, on the GPU part, according to the SNR value, we found GPU has the most contribution to the hardware rendering. And the screen buffer also influences the result, but has few contribution to hardware rendering. We also use the same test on the software rendering, and also according to the frequency and the thread number, we found the CPU contribute to the software rendering, and the screen buffer also contribute to the software rendering. When we test the GPU on the software rendering, we can find that the SNR value is flat. It means GPU does not influence the software rendering. According to the reason, we design and deploy a tag frame, set rendering. Set rendering framework reduces the noise level of the rendering contention channel. The bottom curve is the raw data. we can find a lot of noise on the raw data. Thus, the set rendering framework has two steps to deal with the data. The first step is smoothing. Smoothing adopts a sliding window and applies a smoothing filter. After smoothing, we can find the curve becomes this way. And we also know that the different computer, the different machine has the different rendering capabilities. It means that if we want to use one algorithm to deploy on the different machines, we need to do the normalization. And normalization becomes to top and low reference value. And the curve becomes this style. So we demonstrate the 4 attacks according to our set rendering framework. And because of the time, we just can introduce 2 of them. The first is the cookie cross-browser cookie synchronization. In this attack, we have 2 different parts, the sender and the receiver. The receiver part runs a stable rendering workload, and the sender has the 2 different styles, the high workload style and the low workload style. Just like the example we showed previous, when the sender has the high workload and the low workload rendering task, the receiver, the rendering time of receiver is different. It means the sender transfer the cookie to the binary array and send it to the receiver, and the receiver, according to the rendering time, can know the result. In our evaluation, we found that we test on the different browsers. The sender has the Chrome, Safari, and Firefox. The receiver has the Chrome, Safari, Firefox, and the Tor browser. The Tor browser is not considered to the sender because the Tor browser will clean the cookie after every session. So according to the result, we can find that for the same browser like Chrome to Chrome, the speed can catch the 1.12 bits per second. And for the different browser like the Chrome to the Safari, the speed can catch the 0.56 bits seconds. And the Tor browser is the most hard part. The speed can catch the 0.28 bits per second. So for the next attack is the website fingerprinting. We also need to talk about some background about how the browser rendering a website. It's the incremental rendering. We can take Google as an example. For example, when the browser opens a Google website, it will not rendering everything at the same frame. For example, on the first frame, it just rendering the search bar. And then the next frame, it will rendering the logo. And then it will rendering the click button. And then will rendering the icon. Because for the different frame, it will rendering the different element and has the different rendering workload. It means that we can catch a rendering pattern period according to the website. Thus, we design attack website fingerprinting. We have 2 web pages. Our attack web page will has a stable rendering task, and we also has a target website as we try to infer what it look like. And the right part is the example about the YouTube and Google. We can find their rendering pattern is totally different. In our evaluation part, we also test on the different browsers. We test on the Chrome to Firefox, Chrome to Tor browser, Chrome to Safari. And we compare to the previous side channel, and we can find we has the high F1 score. So for the related work, we list the previous side channel, and our channel is on the bottom. We use the cross-original page. And for the previous side channel, none of them can finish 4 attacks, and our side channel can finish all of them. For the conclusion part, We discover a rendering contention side channel, and we perform a single variable testing for contention cores, the CPU, GPU, and the screen buffer. Also, we design and implement an attack frame set rendering. And according to the set rendering, we demonstrate 4 attacks: cross-browser model cookie synchronization, history sniffing, website fingerprinting, and keystroke logging. So this is a demo about the cross-browser synchronization. And this is our GitHub link and our demo link. Thanks.